Ionic equilibrium deals with equilibrium in solution. Ionic equilibrium introduction. Ionic equilibrium deals with equilibrium in solutions of electrolytes. It explains how acids, bases, and salts behave when dissolved in water, especially when they partially or completely dissociate into ions. Key concepts to cover: 1. Electrolytes and non-electrolytes. 2. Degree of ionization, dissociation. 3. Arrhenius, Bronsted-Lowry, and Lewis acid-base theories. 4. Ostwald's dilution law. 5. Common ion effect. 6. Hydrolysis of salts. Buffer solutions. 8. pH, POH, Ka, Kb, Kw. 9. Solubility and solubility product, KSP. 10. Titrations and indicators. 11. Ionic product of water. Step 1. Electrolytes versus non-electrolytes. For electrolytes are substances that conduct electricity in aqueous solution due to the presence of free ions. Strong electrolytes completely dissociate, e.g. HCl, NaOH, NaCl. Weak electrolytes partially dissociate, e.g. CHCOOH, NH4OH. Non-electrolytes don't dissociate, e.g. glucose, urea. Would you like to continue? Degree of dissociation off. Degree of dissociation of is the fraction of total molecules of a weak electrolyte that dissociate into ions in solution. Formula: alpha equal fracs number of molecules dissociated, text total number of molecules initially present. If C is initial concentration and H pi equals Cr, then for weak acid like CH3CoOH, text Ka equals to C equals C alpha alpha equals Kc. For weak base like NH4OH, frac OH to C equals C alpha 2. Important points. As concentration decreases, alpha. Important points. As concentration decreases, alpha increases. Stronger the acid base, higher the KKB, so higher Fa. Dilution law. This law explains how degree of dissociation alpha of a weak electrolyte changes with dilution. Statement: the degree of dissociation of a weak electrolyte increases with dilution. Mathematical form for a weak acid or base, text K equals C alpha quad, text or alfrac, text K C. Here, K equals dissociation constant of weak acid, initial concentration, fractional degree of dissociation. Implication: if C dilution meishtera, then Eschreikus, at infinite dilution, afaf onester, complete dissociation. Useful trick: if Ka and initial concentration C are known, then H plus alpha C equals C. Shall we move pH? pH equals log POH equals log OH. These are logarithmic measures of hydrogen ion and hydroxide ion concentration. pH scale, pH value, nature of solution at a 6.9, acidic 7, 7.1, 14, basic, relation between pH and POH. At 25 degrees Celsius, pH plus text POH because KW equals 10 French shortcuts. If plus H minus equals 10 squares here, then pH equals 3 tau. If OH man equals 10 and then so pH equals 45 equals 9 ton. Acids like HCl, HNO3, H2SO4 dissociate completely in water. Formula: text pH equals example if HCl is 0.01 mem per then plus squared equals 0.01 to 10 minus 2 right arrow, text pH equals 2. Strong bases like NaOH, KOH also dissociate completely in water. Formula X POH equal OH2 over light hecates, quext pH equals 14, text POH. It's example, if NaOH and 001 M, technically equals 10 equals acid, like CH3COH, weak acids do not fully dissociate in water. Formula text H squared plus equals Ka dot text pH is equals like. Example, if K equals 1.8 times 10 in the French forever minus C equals 0.1 m. Text H equals 1.8 times 10 to the minus 5.1 approx 1.34 times 10 to the minus 3. Right arrow. Text pH log 1.4 times 10 to the minus 3 approx 2.87 partially. Formula text OH squirt KB C dot C quad right arrow quad text. Definition: when a strong electrolyte that gives a common ion is added to a solution of a weak electrolyte, the dissociation of the weak electrolyte is suppressed. This is called the common ion effect. Conditions: 1. One common ion must be present in both solutes. 2. One solute must be strong, like HCl, NaOH, and the other must be weak, like CH3CoH or NH4OH. Examples: 1. CH3COH, weak acid, CH2NA, strong electrolyte, common ion, CH3COH, CH2H dissociation gets suppressed. 2. NH4OH, weak base, plus NH4Cl, strong electrolyte, common ion NH4 minus NH4OH dissociation gets suppressed. Why it happens? By Le Chatelier's principle, if we increase of a product like by Le Chatelier's principle, if we increase concentration of a product like CH3 equilibrium shifts backward, reducing dissociation of weak acid. Buffer solutions. Definition: a buffer solution is a solution that resists changes in pH when small amounts of acid or base are added. Types of buffers. 1. Acidic buffer, made from weak acid plus its salt with a strong base. Example, CH3CoOH plus CHCONA. 2. Basic buffer, made from weak base plus its salt with a strong acid. Example, NHOH plus NH4Cl. Henderson-Hasselbalch equation for acidic buffer for pH equals pKa plus equation for acidic buffer for pH equals pKa plus Cl. Henderson-Hasselbalch equation for acidic buffer for pH equals pKa plus salt acid for basic buffer POH pKb plus log. Important concepts. Buffer works best when salt equals acid base, then pH pKa or pH for POH equals pKb. Effective range pH equals pKa plus 1. Use of buffers: blood pH tie 7.4, biological systems, medicines, industrial processes. Next, 1. Arrhenius theory. Acid, a substance that releases H-PUTs, hydrogen ions, in water. Example, HCl, H- plus Cl mens. Base, a substance that releases O hydroxide ions in water. NaOH, Na plus OA. 2. Bronsted-Lowry theory. Acid, a substance that donates H+ ions in water. Example, HCl, H+ plus Cl men. Base, a substance that accepts H+ ions. Example, NH3 plus H-, N cos. Conjugate acid-base pair. A conjugate acid-base pair differs by one H+ ion. Example, NH3 base, NH5 acid, H2O acid, OH conjugate base. 3. Lewis theory. Acid, a substance that accepts an electron pair. Mnemonic, MDC, multiple bonds, incomplete octet, vacant d orbital. Example, BF3 acid because it accepts electron pairs. Base, a substance that donates an electron pair. Example, NH3 base because it has a lone pair of electrons. Determination. Hydrolysis versus hydration. Hydrolysis, a chemical reaction where water breaks down a compound to form new products. Hydration, a physical interaction where water surrounds or bonds with solute particles. Hydrolysis occurs when the salt is derived from a weak acid or a weak base. pH of the solution depends on the strength of acid and base that form the salt. Types of salt hydrolysis and pH outcomes. 1. Strong acid, strong base. Example, NaCl. No, pH equals 7, K, K, and H, not defined. H was actually an equal tree, pK equals PW for where 2, 2, for pH. Strong acid, weak base, NH4Cl, pH stirred acidic, hydrolysis constant, K equals Kw, Kb, degree of hydrolysis, H frol, equals KVC, inspires C minus my C, H dash at C, and pH 7 minus half, pKb plus log C. Nash 3. Weak acid plus strong base, CH3CONA, pH 7, basic. Hydrolysis constant, KTWKA, degree of hydrolysis H equals K equals 28C equals K to KC equals C and pKa plus log C. 4. Weak acids, weak base. Example, NH2CH3CoO, pH 7 depends on relative strength of acid base. Hydrolysis constant, KW, Ka, K, hydrolysis H, frac H, 1 minus H equals frac K. Definition, solubility product KSP is the equilibrium constant for the dissolution of a sparingly soluble salt in water. It represents the product of the concentrations of its ions in a saturated solution at equilibrium. General equation, for a salt of the form text mxy, right harpoons squared plus ny. The solubility product is given by is the gam times y squared n, where is the concentration of the cations, y meant is the concentration of the anion, m and n are the stoichiometric coefficients of the ions in the balanced equation. If the solubility is denoted by S mole per L, then M plus equals MS quad text and quad Y equals NS. Thus, the KSP equation becomes KSP equals MS squared M times NS squared N